All right, let's dive right into one of the absolute weirdest, most fascinating, and honestly, most profound ideas in all of science: quantum entanglement. And we're going to start with a question that really gets to the heart of why this whole thing is so completely mind-bending. I mean, that sounds like something straight out of sci-fi, right? But this is the core idea we're talking about today. It's a concept that really pushes back on everything we think we know about space, about time, and about reality itself. So to figure out the answer, we first have to understand the connection. So, to really wrap our heads around this mystery, we've got to understand what this connection even is. It's not like there's a tiny string connecting them or some kind of radio signal. No, it's something way, way stranger than that. Something born from the bizarre rules of the quantum world. Okay, so here's the official definition. But let's break that down. Imagine you have a pair of gloves, a left one and a right one. You put each one in a separate box and you mail one box to the other side of the planet. Even before you open your box, you know for a fact that if you have the left glove, your friend has the right one. Simple enough. But here's the quantum twist. With entanglement, before you look, neither particle has a definite state. It's like neither glove is left or right until you measure one. They exist in a weird, ghostly state of both possibilities at once. Now, to really get this, we have to talk about something called superposition. You know, in our everyday world, the classical world, a coin is either heads or it's tails. It has a definite, certain state. But down in the quantum realm, before you measure a particle, it exists in a superposition, which is a fancy way of saying it's in a fuzzy blend of all its possible states at the same time. It's both heads and tails right up until the very moment you look at it. And it's this fundamental weirdness, this probabilistic nature, that makes this whole spooky connection possible. So, how in the world do particles get linked up like this? Well, it's not random, and it's definitely not magic. It happens because of real physical processes. Sometimes particles interact directly, but a really common way is that they're born together in a single event, like when one particle decays and splits into two. Because they come from the same place, they have to obey certain rules, like the conservation of spin. This forces their properties to be perfectly, but oppositely, correlated from the instant they're created. This idea of an instant connection across space, well, it deeply, deeply troubled a lot of physicists. And, it really bothered perhaps the most famous scientist of all time. This wasn't just some quirky little finding for Albert Einstein. He saw it as a direct challenge to his entire understanding of how the universe ought to work. And there it is. This is where we get that amazing phrase. Einstein called it spooky action at a distance. For him, the whole idea that measuring a particle right here could instantly affect another one way over there, well, that seemed to break the cosmic speed limit, the speed of light. He thought it was a sign that quantum mechanics wasn't the full story, that it was missing something big about how reality actually works. So back in 1935, Einstein and two colleagues, Podolsky and Rosen, basically threw down the gauntlet. They published this famous paper, the EPR paper, laying out their argument. They said, look, either this spooky action is real, which violates everything we know about locality, or the theory is incomplete. They proposed that there must be something else going on. Local hidden variables. Think of them like little secret instruction manuals that each particle carries with it, telling it how to behave when measured. In that view, there's no spooky action at all, just information we couldn't see. And for decades, that's where it stood, as a huge philosophical debate. How could you possibly test for secret instructions that are, by definition, hidden? It seemed impossible. But then in the 1960s, a brilliant physicist from Northern Ireland named John Bell came up with an absolutely ingenious way to put reality itself on trial. What Bell did was incredible. He didn't try to prove entanglement was real. Instead, he created a mathematical test, a line in the sand. He proved that if the universe worked the way Einstein thought, with those secret instructions, then the correlations between the entangled particles could only ever be so strong. They had a limit. But he showed if quantum mechanics was right, those correlations could be stronger than Einstein's limit. He gave us a way to actually ask the universe which set of rules it follows. And this table really boils it all down. It's the ultimate showdown. On one side, you have Einstein's idea of local hidden variables, which predicts a very strict ceiling on how correlated these particles can be. And on the other, you have quantum mechanics and entanglement, which predicts that this ceiling can and should be broken. All that was left was for someone to actually build the experiment and see what happened. And here is the mind-blowing result. Starting in the 1970s and getting more and more precise ever since, scientists have run these tests over and over again. And every single time, without fail, they have broken Bell's limit. The verdict is in. The universe is just as spooky as quantum mechanics says it is. The spooky action is real. And Albert Einstein, for all his genius, was wrong about this one. Okay, so this is the first place everyone's mind goes. It's the obvious question. If you can measure something here and it instantly affects something light years away, can you use that to build a faster-than-light telephone? You know, a subspace communicator like in Star Trek? The answer, in no uncertain terms, is a huge, definitive no. And this is a really, really crucial point that trips a lot of people up. The cosmic speed limit is perfectly safe. So why not? How can that be? Well, there are a few key reasons. First, even though my measurement is perfectly correlated with yours, my individual result is totally, completely random. I can't force my particle to be spin up just to send you a 1. I get what I get. Second, because of that randomness, I can't actually send any controllable information to you. And finally, and this is the real kicker, the spooky correlation is totally invisible to each of us individually. We only see the amazing pattern after we pick up the good old-fashioned telephone, which works at the speed of light, and compare our lists of random results. So, you might be thinking, okay, if we can't use it for faster-than-light communication, what's the big deal? Well, it turns out this thing that was once just a philosophical headache is now being harnessed as an incredibly powerful resource, one that's driving a whole new technological revolution. We're learning to use entanglement as a core component in quantum computers, machines that can process information in ways that are just impossible for any classical computer. They could help us design new medicines or create revolutionary materials. We're using it to build quantum cryptography systems that are, by the laws of physics, completely unhackable. And yeah, we're even using it for a type of quantum teleportation. Now, we're not beaming people around, but we are transferring the delicate quantum state of a particle from one location to another, which could change everything about computing and networking. But there's a catch, and it's a big one. Entanglement is unbelievably fragile. The tiniest interaction with the outside world, a stray particle of light, a little bit of heat, can instantly break that special connection. This process is called decoherence, and it's the #1 reason we don't see entanglement happening with big things like cats or baseballs. It's also the single biggest engineering challenge for scientists trying to build all this new quantum tech. So, let's just pull this all together and recap the key takeaways. First, entanglement is absolutely real. It's a fundamental feature of our universe. Second, it does not allow for faster-than-light communication, so Einstein's theory of relativity is safe. Third, it's actually the key ingredient for all these amazing future technologies. And finally, it's no longer seen as a paradox. It's just a deeply weird but totally accepted part of how reality works. And that really just leaves us with this final incredible thought. Entanglement proves that the universe isn't just a collection of separate, isolated things. No, at the deepest level, it's all profoundly interconnected. And if a reality this strange has been hiding in plain sight this whole time, it just makes you wonder, right? What other profound secrets is the universe still waiting to show us?